$30 to do first day of class. You get there kind of early and just when's this guy gonna show up?
I believed in you without seeing them. So that counts, right?
Professor's not coming on. I think that's sort of a line.
You want to come double check me real quick?
This guy's gonna show up out this week.
Okay, so your host, right? Great thought, Jim. Member story, Brad's here. Then skeptical sidebar by Mark. And then I've got astronomer, comma, guest speaker, Dr. Scott. Right?
You have this chair.
Yeah. He'll be the free Burn. So at the end, when you normally shout out like how to get in contact with us, I'll be the host. Yeah, I'll come back around. Okay. When you do, did you make a thing? Just have this, how to become an official member.
And that'll just be visible to the people online.
While you're talking, I'll be putting that on.
Pretty cool. Okay, so I don't even necessarily need to know that, but just know that
When you get to that point, I'm just gonna really quick. You can be talking about anything. I'll just keep laughing. When you call out meetup, I've got a meetup link. If you go to audio, if the audience is and then the blue mic is on Dr. Austin, the green mic is on
And then I've got those handheld up there in the chair that burns for power speakers. So that was the probably make it crank it right.
I don't have a way to get it in.
Yeah, no way to get from that.
Yeah.
So
And it's all usually people ask their entire question and then we hand them the paper so they work their
yeah.
like it's not a big deal.
Yeah. Maybe I'll mention something about Q&A afterwards and you'll be asked that again. And then I'll crank that mic super high so it's like,
I don't think that's not the way. Yeah. As long as people enunciate in the room, it should be okay.
What, it used to be, I guess every 2 years. I didn't realize it expired. What's not?
1 minute.
do you want to tell me go? What's time to go?
1 minute.
Yeah, well,
think the turnout would not be so great last weekend, but you know, we roll with it. Welcome everyone to the Arkansas Society of Freethinkers monthly meeting. ASF is a nonprofit organization devoted to separation of church and state and building secular community. You can find more about us online at arfreethinkers.org, including a calendar, or you can go to meetup.com/arfreethinkers to find our calendar. And because I'm a nerd, I have the Meetup app on my phone where I can just easily look up what the upcoming meetings are. We have stuff coming up this week, actually, if you'd like to continue the conversation. ASF is a diverse organization made up of many different viewpoints. Our speakers may or may not reflect the opinions of ASF or its individual members. Bathrooms, if you need them, are to the back and to the left. And I'll ask everybody to silence their phones and go, because here we are going to learn some enormously useful things today. Our first order of business is the free thought of the day. And giving the free thought of the day today will be our own infamous Jim Lindsley. Let's give him a hand.
And Supreme Toastmaster style, you come here. Hello, sir. Well, I just have to read something. Thank you for this joyous occasion for me to begin the first speaker. And I have it written down on my cell phone here, about 3 miles long. I'm just going to recap it. And basically what it is, sorry, I've got a dead cat in my pocket. If anybody knows what a dead cat is. But anyway, I don't know if you know this or not, but I'm getting older, and probably some of you guys are getting older too. And the situation we are in right now with our country it's very fragile. Very fragile right now. I like the way you're looking at me there, Sherry. And we have people, I'll do this. We have people that are going to Canada. But it's a really dire situation in my opinion. And we have, my parents, my dad was in World War II, and I have lots of uncles that were in World War II, and they did something special for us, and that is they gave us a country, an economy, and a way of life that we enjoy here, at least we have in the past. And it's up to us to kind of keep that thing going forward. And very briefly, if we don't work and work on keeping what we have and working on improving what we have, then the very basic line and the bottom line is that we are going to be defrauding our parents and our grandparents who fought so hard. I don't get choked up about this at all, but I don't think we really realize so much. I mean, we spend all our time here enjoying the things that we have, that we can do, but we just don't realize that this began, a lot of it began back in the 40s when our parents sacrificed so much for us. And that's about all I have to say.
Thank you, Jim. Next up, we have Member Story by our own Brad Erickson, who is going to tell us about an important holiday that you probably let pass by without even thinking about it. So let's give Brad a warm hand.
How do we get this in here? I think it went in there.
Oh, sorry, I didn't realize that slides.
technical difficulties. One moment. There. Is that it?
And then I don't have my glasses.
Biological difficulties. One moment.
Okay, where are you?
We have had presentations before where it was literally, it's been a long time. Like, hold up your sheets.
Come on, open.
And calculators sure did deep slide rules. What's that? Calculators sure did deep slide rules.
That's true, yeah. Well, where did it go?
Logistical difficulties, please hold.
I thought I opened that folder, and now I don't see it at all.
It might be. Wait, again, you can scroll down a little bit.
Oh, did it not save it? Oh, good. Should be labeled Darwin Day.
Let's switch places with you and Vern. It should be labeled Darwin Day, you're saying?
Yeah, should be labeled Darwin Day. There it is. Okay.
Yeah, bring me into the camera.
Patience. So yeah, who else was born on this day that you should know about? Nope. Abraham Lincoln. There we go. So Abraham Lincoln and Charles Darwin, both born on February 12th, 1809. And it's interesting to note that Abraham Lincoln was the individual that established the National Academy of Sciences in the United States. And so as a result, I always see Darwin and Lincoln as sharing a love of science. Okay, so I want to start out by just talking a little bit about Charles Darwin. He was born, as I just described, February 12th, 1809. And he was a bit of a prodigy. He entered med school at age 16. Okay, so in Edinburgh. But that really wasn't his calling. He rather quickly changed educational course and decided to enter the clergy at Christ College. A lot of people don't know that Darwin actually went into the clergy for a little bit. I've got one other little side note up there. He learned taxidermy from a freed black slave. And the reason I bring this up is that creationists like to paint Darwin as a strict racist. He was no more of a racist than anyone in his day. Okay, and the fact that he would take lessons from a freed black slave kind of emphasizes that. Now, while at Christ College, he occupied the very dorm room that was occupied previously by William Paley. Anybody know who that is?
Man at paleontology.
No? Richard?
Isn't Paley the one who talks about the pocket watch?
Yes, yes. So William Paley is the originator, shall we say, of the watchmaker argument.
The creator of the argument.
Right, the creator of that argument. And the argument goes like this. If you were walking along a beach and you found a watch, you picked it up, the complexity of the watch would suggest a watchmaker. Okay, and hence that's why you hear that argument many times still today from creationists. Then in 1828, he attends John Henslow's botany lectures, and it was at this point that he became extremely passionate about science. This is what really got him going, turned him to a full-blown naturalist. Then in 1831, he graduates from Cambridge, and then later that same year, he begins his famous voyage on the HMS Beagle. And of course, during that time on that voyage is when he makes his tremendous amount of observations that leads him to formulate the idea of evolution and subsequently the theory of natural selection. Let's see. Next slide. Okay. Then, once that voyage is ended, he gets back. He spends the next 29 years formulating how evolution works. And during this time, of course, is when he's putting together the work that will ultimately be published on the is that on June 18th, 1858, he receives a letter from Russell Wallace in which Wallace, in essence, describes natural selection. So Darwin was not the only person to come to this conclusion. All right? And in fact, it's that letter that is often credited to getting Darwin off his butt, if you will, and finish writing on the origin of species. So in November of 1859, Origin of Species is published, and that first printing, the entire set of books from that first printing sold out in one day. I imagine there's a few of you that would love to write a book and have all copies sell out in one day. Okay? And then on June 30th, 1860, the famous Huxley-Wilberforce debate takes place. Now, Samuel Wilberforce, Reverend Samuel Wilberforce, was a staunch creationist, and Thomas Huxley was known as Darwin's bulldog, and they had a very heated debate, and I want to skip to one aspect of that debate. Okay, so during this debate, Thomas Huxley famously answers Reverend Samuel Wilberforce's question of whether it was his grandmother's or grandfather's side that was an ape, with the following response: "A man has no reason to be ashamed for having an ape for his grandfather. If there were an ancestor whom I should feel shame in recalling, it would be a man of restless and versatile intellect who, not content with and success in his own sphere of activity, plunges into scientific questions with which he has no real acquaintance, only to obscure them by an aimless rhetoric and distract the attention of his hearers from the real point at issue by eloquent digression and skilled appeals to religious prejudice. Given the choice between such a man and an ape, I unhesitatingly choose the ape." Darwin died April 19th, 1882. He was buried in Westminster Abbey next to a rather famous other Englishman scientist, Isaac Newton. And so I'll finish by giving the final quote in Origin of Species. "There is grandeur in this view of life, with its several powers having been originally breathed into a few forms or into one. And that, whilst this planet has gone cycling on according to the fixed law of gravity, from so simple a beginning, endless forms most beautiful and most wonderful have been and are being evolved." Thank you. Okay. Can I just take this out, or will that mess things up?
Yeah, sure, go for it. We're not afraid of technical difficulties down here at all. We go bravely forward. All right. Now, when I said that you guys had probably let a holiday slip that you should be paying attention to, how many of y'all thought I was talking about the Hershey's Corporation holiday? No, I wasn't. Okay. Our next speaker is doing Skeptical Sidebar, and it is our own, also infamous, Bern Bradley. Let's give him a warm welcome. Don't tell me you have slides.
I do. So you need to do something different?
All right, yeah, we gotta get these
But
loaded.
those are not mine.
You can get my top.
If the slides are real nice, I could probably. Let's see. There we go. Oh.
My slides are cuter than mine.
Now, let's see. If I do that. That's just something that I created for a Valentine's Day card. Has nothing to do with today. This is our topic for today. Show of hands, how many believe that you can flush bathroom wipes? Yep. Two in a group.
Are you talking about toilet tissue?
Bathroom wipes. Wipes. Now, I had a long discussion with my father, who's 92, about 4 years ago, and told him, you can't flush these. He said, it says flushable on it. I said, plumbers did that because they needed the business. And I'm not sure he ever believed that, but he quit flushing them, put them in a little trash can. It did a couple of weeks ago, I got a podcast where they explored this very thing. This is a grate at a sewer, and what happens is everything that goes through the sewer that's solid, that by the time it gets to the sewer plant is not dissolved, gets caught in these grates. They did a survey. The people that make the washes, the wipes that say flushable on them, they say you can flush ours because they degrade. The city sewer people say, no, you can't. It kind of turns out that they're both a little bit right. But they did a study where everything that got captured there, it has to be pulled out and handled as solid waste. If it won't go through that, they rake it out and handle it as solid waste and send it to the landfill. What they discovered was that the wipes that say flushable on them, that when they pulled all the wipes out that wouldn't degrade, all the ones that were made intended to be flushable accounted for 1% of the wipes that were caught in the grate. So they really do degrade, and they degrade fairly well. But here's the difference. White cloud. It reminded me of the old, it's how things have changed. They used to not be able to say the word on television, and then finally, White Cloud came out with a commercial where they had a lady saying, White Cloud doesn't feel like toilet paper. But this is what happens to toilet paper when it gets into water. It just goes apart. Does it matter? Toilet paper doesn't matter how much you flush down it. Enough water goes through it, it'll come apart. Not necessarily with the wipes. The conclusion of the people doing the study was if the wipe says do not flush on it, baby wipes almost all say do not flush. Almost all of them say that. And it's because they use a lot of oils in them. The ones that say flushable are pretty good. 1% of them are probably not going to degrade. But by the middle of 2026, the industry has accepted new standards so that anything that says flushable is going to be flushable. And this was a remarkable, this was to me was interesting. And what caused this, what caused the podcast to take this on, was that a guy wrote in and said, I buy these and my girlfriend doesn't like me flushing them. What do you think? And that's the answer. Thank you.
Thank you, Bern. And if there was any ambiguity there, flushable is a lie. It will cost you hundreds of dollars one day to have that habit. And I'm not sure if I'm going to believe them after 2026, having been lied to for over a decade now. All right, so you've just heard member story and skeptical sidebar. These are options that you can take advantage of if you would like to give a presentation for our ASF monthly meeting. Just give us a shout, one of the officers around here, and we'd be happy to sign you up if you have an area of expertise or an area of experience or something important that you'd like to share or know somebody. Then we're always looking for opportunities. Now, on to the main event. Good job, y'all. Dr. Scott Austin is our resident astronomer at the University of Central Arkansas, and his bio and intro has been lost by me. Memory difficulties, I suppose. But he has a long and illustrious history of working with the planetarium and the telescope there, and we had a big presentation with the solar eclipse last year, no, the year before that, and basically he knows his stuff and we ought to listen. And if you're wondering what has happened with the James Webb Space Telescope since the last time you heard about it, and since it's been streaming just probably petabytes of information back to Earth all this time, Dr. Scott Austin is here to hopefully inform us about some of that. So let's give him a warm welcome, Dr. Scott Austin.
Thank you, Chris. All right. Thanks for having me. Technical difficulties. There we go. All right. Thanks.
You're getting good at it now.
Again, thanks for having me. The mission today is kind of do an overview of the James Webb Space Telescope, which is currently the largest space telescope to date. Give you some background on the telescope itself and some of the preliminary results of the James Webb Space Telescope. It went up in 21. There was some commissioning that had to be done, and then since then they've been getting a variety of different results. This isn't going to be inclusive of all the results that have been found so far. The other disclaimer is this isn't my work. I've not worked on any of the James Webb Space Telescope data, but thing to keep in mind about things like the Hubble Space Telescope and James Webb Space Telescope data or any other US-based space telescopes, that once that data has been gotten a year later, that's open to the general public. So the Hubble Space Telescope archive, anybody can get on there and download the data. Now it's going to be raw data and you got to know what to do with it, but it's available to the world at that point. So the principal investigators get exclusive rights to it for the first year. So the major science areas of the James Webb Space Telescope generally fall into these categories. Either the early universe, galaxy evolution over time, star formation, exoplanets, and then targets within our own solar system are the major science objectives. So probably the most famous space telescope to date is the Hubble. And the primary mission of the Hubble Space Telescope, and thus the name of the Hubble Space Telescope, was to determine the Hubble constant more accurately. It's not the only thing the Hubble Space Telescope has done over time. One of the things that the James Webb is trying to accomplish is to add on to that and to improve that measurement as well. So let me kind of give an overview of the James Webb Space Telescope. Now over the decades, there's been lots of space telescopes, probably a number of them that you've not heard of. Of course, the Hubble is the most famous of the space telescopes. The Hubble can observe over the visible light wavelength range into a little bit of the ultraviolet, into a little bit of the infrared in terms of the spectral coverage. So if you heard that the James Webb Space Telescope is the replacement for the Hubble, it's not exactly a replacement, because the James Webb, as you can see there, it's not a visible light telescope, it's an infrared telescope. So it looks at wavelengths longer than visible light. It's not the first to do that. There's been a number of infrared orbiting telescopes. There was one of the early ones that the US put up was called IRAS. The one that you're seeing there called the Spitzer was the more recent one, and then now we've got the James Webb Space Telescope. You can see the Spitzer covered more of what we call the far infrared, longer infrared wavelengths. So shorter than radio waves, but longer than visible light. As an analogy here, one of the things that Christopher Hitchens used to do in terms of an argument to people was that he'd tell Christians, you're an atheist except for one God, right? You're blind except for that narrow range of wavelengths. So much of the universe is invisible to your eye. So wavelengths that are longer than that, you cannot see with your eye. Shorter than that, you can't see with your eye as well. So one of the things astronomers want is they want full coverage. They want to be able to see the universe from gamma rays to X-rays, ultraviolet, visible light, infrared, microwaves, radio. That's the only way you can get a complete picture of what's going on in the universe, because there's different phenomena that happen at different energies. And if you want to look at cold stuff, it's going to be emitting at different wavelengths than hot stuff. And so you need that sort of coverage. So you can see the James Webb Space Telescope fits a niche there in terms of the wavelength coverage that astronomers want in terms of the universe. Why a space telescope? When it comes to infrared, for the most part, you need to get above the atmosphere. Now, there are certain wavelength bands that you can do a little bit of infrared from the ground, but not a whole lot. The Earth's atmosphere does a really good job of blocking a lot of infrared light. So if you want to, especially in the far and mid-infrared range, you really need to get above the Earth's atmosphere. That electromagnetic radiation isn't getting to the ground, so you really have to get above the Earth's atmosphere. And then you can see, you can do radio from the ground, but pretty much all those other wavelengths you've got to do from Earth orbit. Now, there's some advantages in the visible getting above the Earth's atmosphere in that you don't have the Earth's atmosphere blurring your images and doing a little bit of diffraction and things like that. So again, it's a space telescope because it really has to be. Elsewise, you're going to be blind from the surface. For comparison, this is what the James Webb looks like, the picture diagram at the top, and it's being compared to what the Hubble looks like on the bottom there. And so you can see from the stats there, the aperture of the James Webb Space Telescope, it has about a 6.5 meter diameter. Now that's actually kind of small for some of the largest ground-based telescopes. We got ground-based telescopes that are 10 meter class and above that are coming online. But for a space telescope, this is the largest so far. You can see the Hubble has an aperture about 2.4 meters. So in terms of light gathering capacity is a function of surface area. So if you compare 6.5 meter to 2.4 meter, that's 7.5 times the light gathering capacity of the Hubble. So that means you can look at things that are dimmer because you've got more light gathering capacity. The other thing that aperture does for you as well is it makes your images sharper. You have better resolution as you go up in diameter as well. And with both of these above the Earth's atmosphere, they don't have any of the blurring effects of the atmosphere that helps you there as well. Mentioned the Spitzer. That's what the size of the Spitzer mirror was, less than a meter. Now, let me go back a little bit. You'll see that the James Webb collecting mirror there looks a little funky because it's not a single mirror, it's an array of mirrors. This is some technology that has actually shown up in ground-based telescopes. We have a number of multiple mirror telescopes. If you look up the Keck telescopes that are in Hawaii, these are 10-meter class. They look much like this. They're hexagonal mirrors that work together for a single mirror. So this telescope is just amazing in terms of the amount of complexity and technology in it. To launch a telescope that has a 6.5 meter diameter, you need to do some origami, right? This thing was all folded up, which is the other reason why you have these hexagonal mirror segments. This was all folded up, put in the nose of the rocket before launch. And so it's just amazing that everything worked on deployment, that everything opened up properly. The thing that looks like a kite on the bottom, that's basically a sun shield, that had to work properly. So this is just an amazing piece of equipment. So again, the mirror is the hexagonal sections there. That sends the light to the secondary mirror out front. That sends it back to the hole in the middle. It goes through the hole, and that's where all the instruments are located. So there's a number of different instruments in there. Now, where is the James Webb Space Telescope? I've run across the misconception that some people think we send like the Hubble and these telescopes to places. No, these are telescopes in the solar system, still not terribly far away from the Earth in terms of astronomical distances. So Hubble is a low Earth orbit location. That was put up with the space shuttle. Space shuttle, you're looking at 200 miles or so in terms of the height above the ground. The Webb is out beyond the moon at a special point called the L2 point there. And let me zoom out here. These L points are called Lagrange points. If you've heard of something called the three-body problem, the two-body problem, you can use Newton's mechanics, and for two objects orbiting around one another, you can, with pencil and paper, get a solution to that. So elliptical orbits, circular orbits, all of that you can do with pencil and paper. Now, if you got two objects and you introduce a third, and let's say we got two large objects and a tiny third object, you can't solve with pencil and paper what the trajectory of that thing's going to be. Except for these points. These are the Lagrange points. These are the stability points, where if you park an object at those orbital locations, they will stay there. So if you imagine, this is all in motion. So the system that we've got here is the sun, and the Earth is the main gravitational system. And so the Earth is going around the sun. And so if you imagine taking this diagram and rotating it, for example, that L2 point is always going to be opposite the sun along that line as it goes around. So everything's in motion here, but that L2 point is going to be in that location relative to the Earth. Same with the L4 point, the L5 point, and the L3 point. We were making fun at lunch about, are you old enough to know? Anybody remember the L5 Society? He knows what I'm talking about. So the L5 Society was, their mission was, or what they were advocating was to put a habitat at L5 in this system, where they had elaborate systems of taking materials from the moon, mine the moon, put a space station, not more than a space station, but a big habitat at that L5 position. So that's where they got the name. It was that Lagrange 5 point. But anyways, the James Webb, where it lives, is out at that L2 point. Now, it's not right at the L2 point. It actually orbits that L2 point. So if you put this in motion in your head, it's going around that L2 point, and then that L2 point is moving with the Earth. Now, the L2 point is a good place to put this because you want protection from the sun. And you also don't want any interference. You don't want to look at the Earth and the moon with this. So you don't want any sort of interference from that either. So you can park it out there. And then the other thing, I'll talk about infrared light here. You want to be able to cool your telescope and your instruments down to low temperatures. Let me kind of go forward here a little bit. If you've got an infrared camera and we pointed at all of you, and we turned off all the lights in here, you're all glowing in the infrared, okay? So imagine an optical telescope that is glowing in the optical. Hard to do astronomy, trying to detect light that your telescope is emitting, right? So infrared telescopes are cooled to very low temperature. As you lower that temperature, you're going to cut down on the amount of infrared emission. And so that Spitzer space telescope that I showed you earlier, that was a big thermos bottle. That thing was launched with liquid helium in the thermos to cool it down. What happens to your coffee, your hot coffee that you put in your thermos if you wait long enough? It's going to cool down. Or vice versa, if you put iced tea in your thermos bottle and wait, it's going to warm up. That Spitzer had a limited lifetime because of that. Eventually, that telescope warmed up, and you can't do infrared astronomy with it anymore because now the telescope and the instruments are glowing in the light that you're trying to see. So with the James Webb, this is not in a thermos bottle of liquid helium. What they did is they sent along an umbrella. Okay, so you got this sunshade, and so you put the sunshade facing the sun, and then you got the telescope on the other side, and then you wait. Because they couldn't use the telescope right off the bat once they got out to L2. They had to wait. If you wait long enough, it's going to radiate that infrared, and the temperature is going to come down, and the temperature is going to come down to the temperatures that you want. You can see in terms of Fahrenheit, minus 388, minus 233 centigrade is what that's going to cool down to. Now you're at operational temperatures. And as long as you have that sunshade working, you're good. So this does not have a limited lifetime because you're taking liquid helium with you. Okay. So the telescope, once it's collected the infrared light, there's a few different instruments on board that they can take that light and shove that light or the infrared light into those various instruments. So there's the NARCam, or near infrared camera. So it can take images, is one of the things it can do. It can also get what we call spectral information. So even within that near infrared range, it would be nice to be able to measure what the brightnesses of things at different wavelengths within just that range. So it can do a little bit of that too. It can get us some spectral information there. It also has the ability to block out stars. The thing that they're calling a coronagraph there. Let's say you want to be able to get an infrared detection of a planet around a star. Well, a star is going to be pretty bright. This has the ability to block out the light from the star so that you can see what's going around the star and be able to see something that's much dimmer. So it has that capability as well. Again, for the near infrared, you can see the sort of wavelengths that they're doing there. So it's just a bit longer than visible wavelengths. So again, it can do imaging. It can get a little bit of spectroscopic information as well. And then the other camera is the mid-infrared. So longer wavelength than the near, but not out where Spitzer was operating. And similar capability in terms of doing imaging and getting some spectral information. This one can do more straight up spectroscopy. So if you imagine in optical where you take a prism and you make a rainbow, they're doing the equivalent, but the rainbow is in the infrared instead of the visible. So it can do that as well. And then the third camera or instrument is more straight up a spectrograph, where instead of getting an image, you're getting graphs of brightness versus wavelength with that. And so a lot of these have both imaging and spectroscopic information that you can get. Most of the science, even with the Hubble Space Telescope, doesn't come from the pretty pictures that you see. The pretty pictures are nice. There's certain things that you can do with the pretty pictures. The Hubble Space Telescope has spectrographs on it as well. Now, if you can take that light and spread it out into its component wavelengths, you can figure out things like composition, temperature, speeds. There's a whole number of things that you can do that you can't do with just images. But a lot of the things that you're going to see in terms of press releases are the pretty pictures. But just keep in mind, that's just the tip of the iceberg in terms of the science that things like the Hubble and the James Webb does. Let me see. So again, these are our major science areas. So I'm going to do a bit of an overview here of some of the early significant results that they've gotten. And we'll start furthest away and furthest back in time with the early universe. So we'll start there, and then we'll work our way closer and closer to home into this. And then we'll get to the restroom like we did earlier, but if we need to. But so early universe. So telescopes, you can think of them as being time machines. The further away something is, the further back in time you're looking, because speed of light is finite. It takes light a certain amount of time to get to you. So when you see the sun, you're seeing it 8 minutes ago. Okay? The nearest star to the sun is 4 light years away, which means it takes 4 years for that light to get to it. So you're always seeing things on a delay. You're seeing a delay now, but it's really tiny here because of the speed of light. But you get to large distances, you're looking back millions, sometimes billions of years into the past. And so that's one of the goals of the James Webb Space Telescope, is to push the distance back in time and space in terms of what we're able to see. So in this diagram here, on the right, that's representing the universe now in our local neighborhood of the universe. Things that are, I say local, but things that are mere millions of light years from us, okay? And then as you work your way to the left, you're working further away from us and further back in time. Now, the furthest light that we can see is that afterglow pattern that they're talking about there. That is seen with microwave telescopes. That's as far back in time as we can see, because you're looking back to a time before stars and galaxies, a time when the universe is filled with ionized gas, mainly hydrogen, a little bit of helium. And so with telescopes, you can't see the core of the sun because the sun is mostly ionized gas. So if you're looking at a plasma, light can't travel very far through a plasma, okay? So that's as far back as we can look. Now, the Hubble, and I'll put up another diagram here in a moment that will do this, but the other thing to notice about this diagram, as you go back in time and space, we see galaxies. We see more galaxies. We see more galaxies. What we've not until really now been able to see is galaxy formation. The galaxies that we see, they form pretty much at the same time in the universe. As opposed to star formation. Star formation is happening as we speak in our galaxy. It happens continually. Galaxy formation happened once in the history of the universe. And so Hubble can't quite see far back in time enough to see galaxy formation happening. And so that's one of the big missions of the James Webb, is to be able to try to see that first era of star formation and galaxy formation. So let me put this is a similar diagram here. It's also putting some numbers on there. Up top, you've got time since the Big Bang. So now we're nearly 14 billion years after the start of the Big Bang. Down below is redshift, which I haven't mentioned yet. The other thing, the further away something is in the universe, the more redshifted its light is going to be. Okay? That's going to have an impact on why they chose an infrared telescope. Okay, and I'll talk more about that. But as you go back in time and space, the light is going to be more and more redshifted. So redshift, that's going to correlate to how far back in time we are. So you can see a redshift of 10, you're back to over 1 billion years ago in terms of the timeline on the universe. So let me step up here. The Hubble can kind of get us back to here. What we want to do with the James Webb is get back into there. And if possible, back to here, to the first star and galaxy formation. Okay? So we can see the background radiation, the recombination there. We can see, we're trying to fill in the middle there in terms of galaxy and star formation. Let me talk a little bit more about why redshift. Okay? Now, tornado season, and you're watching the weather, and they're using Doppler radar. They're doing red shifts and blue shifts with the Doppler effect. This is not the Doppler effect. This is another way you can change the wavelength of light. This is something Einstein pointed out in his theory of general relativity. So, actually, let me step back a little bit here. The reason this diagram is flared out like that is, you may know, the universe has been expanding since the start of the Big Bang. Okay? Space itself is stretching. Now, Newton was mentioned earlier. Newton didn't see the universe like that. The universe saw space as being a nothing. Well, not Einstein. Einstein says, look, space is a something. It has dimensions. It has geometries. It can be stretched and squished. So the history of our universe is this expansion history. So as the universe expands, the light, during its history, if it's traveling for 13 billion years to get to us, during that travel time, it's getting stretched with the space. So you may have a photon of light that's starting out as an ultraviolet photon that could give you sunburn. By the time it gets here, 10 billion years later, it's no longer an ultraviolet photon. It's going to be out in the infrared. So not only are things far away in the universe going to be dim, they're going to be redshifted, and so chances are they're going to be brightest in the infrared. They may not have been brightest in the infrared when that light left that distant galaxy, but it's going to be brightest now by the time it gets to us. Okay, so that's why infrared. There's going to be some other reasons why infrared that I'll show you for things that are closer to us, but for early universe, infrared's the way to go because of the cosmological redshift. So again, this is demonstrating you start off with maybe an ultraviolet photon. By the time it gets to us, it's going to be an infrared photon. So we want to be able to see the furthest away galaxies we can. So the James Webb is starting to catalog some of those. So this galaxy here, or protogalaxy, is at a redshift of about 14. We're looking at about 3.5 billion years ago in terms of look back time. Or in terms of the start of the universe, you're looking at a baby picture here of a galaxy about 280 million years after the start of the Big Bang. Okay? Now, that's something the Hubble can't do. You're still not seeing a whole lot of detail there, right? Guess what astronomers are going to ask for next? To really, I think to really answer some of these things that we're going to touch on, you need a bigger telescope than the James Webb. You want more light gathering capacity. You'd like to get more resolution. You'd like to be able to see these things better. We're at the point where we can detect them, and through spectroscopy we can make measurements of redshift and composition and things like that. There's things that we can still infer, but we would really like something even bigger, right? 20-meter telescope, 30-meter space telescope. So these are some of the most distant ones that in the data so far. Is redshifts around 14, and the one debate that you may have been hearing a little bit in the news about galaxies at these distances and times, they're a bit brighter than people were predicting. In other words, these seem to be larger than people were predicting. So at some point you have galaxy formation happening. How long does it take to form a galaxy? And it looks like maybe it goes fairly quickly, or quicker than people were modeling. Okay, people have been modeling this stuff for a long time now. They've had no data until now. Now we got data to check those galaxy formation models with. The other thing that they're seeing in the early universe are evidence of supermassive black holes. So if you look at galaxies in the universe today, our own Milky Way galaxy, the Andromeda galaxy, pick a galaxy, it's going to have a supermassive black hole in it. I'm talking millions, sometimes billions of solar masses. How did they form? People have been trying to model that. Well, we're seeing evidence for supermassive black holes fairly early on too. So I think people are going to have to go back and work on their models in terms of galaxy formation, supermassive black hole formation. So, and so that's one of the things that you may have heard a little bit in the news about one of the discoveries of the James Webb. Is it looks like galaxy formation and supermassive black hole formation has happened faster than what people were predicting. Now, if I go back to here, if you can go and look at galaxies at different times, you're actually getting a record of how galaxies evolve over time. Again, we're trying to figure out the earliest part, the formation part, but how have galaxies after they form changed over time. And if you look at galaxies at different distances, you're getting a record of that. And so that's one of the things that they've been looking at. And going back to fairly early in the universe, they're seeing galaxies that don't look anything like galaxies we see in the universe today. So they've got a class of something that kind of looks like it's probably galaxies, but they don't have any of the characteristics that you normally see in terms of the spectrum of galaxies and things like that. So how do these fit in? They're going to have to figure out exactly what these are. Are these proto-galaxies? Is this a stage galaxies go through? These tend to be quite compact objects. If you've heard of something called a quasar, quasars are a type of galaxy that's way back in time as well. that has supermassive black holes in them and are very energetic objects. These seem to be compact, but they don't seem to be quasars. So are these similar to quasars, not similar to quasars? You know, how do these fit into galaxy evolution, galaxy formation? So these things weren't predicted, which is often the case. When you have a bigger telescope or when you're looking at stuff at different wavelengths, you end up finding stuff you didn't predict. And this is an example of that sort of thing. Similarly, there's these little red dot galaxies. They tend to be fairly compact as well. And so they're trying to figure out, again, how are these fitting in? Now these aren't, notice these aren't at as big a redshift. These aren't as far back in time. So is this a phase that galaxies go through in terms of their evolution over time? Again, we don't see objects like that millions of light years away. You got to go back over 1 billion light years or so to see that. One of the, as I mentioned earlier, one of the major missions that got the Hubble funded was to accurately measure the Hubble constant, which is a measure of the rate of expansion of the universe. There's different techniques at getting at that. It involves measuring distances. And measuring distances, you like to have something that you know the intrinsic brightness of, so that when you observe it and you see how dim it is, that dimness is due to the distance. And so there's a handful of things that you can use. There are something called Cepheid variable stars, and they vary in brightness, and how fast they vary in brightness is correlated with their wattage, their intrinsic brightness. And so you can use those as a standard candle, and then how bright they appear, you can figure out the distance. So that's one of the things that Hubble did. Hubble was looking for Cepheid variable stars in galaxies and using that technique to get an accurate measurement of distances to galaxies. The other standard candle that often gets used are supernovae, especially type 2 supernovae. And they get to a known brightness. So you have a standard candle, measure how bright it appears to be, you know the wattage of it, you can figure out the distance. What they're running into, and if you've heard this in the news, something about the Hubble tension, they're not getting consistent results between the Cepheid variable measurements for the expansion and the supernova expansion. And the James Webb Space Telescope has observed some very distant supernovae going off in these very distant galaxies. And so they're not getting, there's something that's not squaring. You're not getting the same measurement of the Hubble constant with those two different techniques. Now, one of the things that they're doing in terms of measuring distances for these supernovae is there's a way to magnify things in the distant universe sometimes. You don't have any control over it, but there's an effect called gravitational lensing. Again, like I said earlier, space can be bent, squished, that sort of thing, and then light has to pass through it. If light is moving through curved space, it's not going to go in a, quote, straight line. It'll go kind of like a lens in this case. So if you've got a massive object that is curving space-time, and you've got an object over there to the left that's emitting that light, when it passes through that gravitational field, that light's going to change direction. Now you think the light is coming in a straight line, so you think the object is over there at the apparent position when it's actually in behind the object. So now it's not only does it change the position on the sky of where the thing is, it can also distort it in a way to make it brighter. And they've done that with the James Webb. They found some gravitationally lensed galaxies with supernova going off in it. That brightens it, makes the measurement easier to do. Related to this is all these arcs you're seeing, those are those apparent images of those more distant galaxies there. Okay? Now, the galaxies you see in the foreground, they're the ones curving space-time to cause that funhouse mirror effect there. Now, the amount of curvature is due to how much mass is in the foreground here. If you add up how much mass is in the foreground, you shouldn't get that much gravitational lensing. And if you've heard of something called dark matter, this is one of the evidences for dark matter. Okay? So this is a James Webb Space Telescope image. You can, from how much things are distorted in that image, you can infer how much mass is in the foreground. Not only that, you can map out the dark matter, the stuff that you can't see that is contributing to the curvature of space-time. And so the blues here that you're seeing, those blue splotches, that's the inference of dark matter due to the distortion of the background. And so some of this was done with the Hubble, but since James Webb is bigger in diameter, it has higher resolution, you can get more detailed maps of that dark matter. So you can see you're seeing less detail on the left and a lot more detail on the right in terms of the dark matter. And so dark matter, we don't actually know what it is. Matter may not be a good description of it. What it is something in the universe that's curving space-time. That's basically pretty much all we know for the most part. The other thing that we know a little bit about is how the dark matter interacts with itself. Now, a few years ago, you may have seen this in the news, something called the bullet cluster. So on the left, you have a cluster of galaxies. On the right, you've got a cluster of galaxies. And when you map out the hot gas that's between the galaxies, and then map out where the dark matter is using that funhouse mirror effect due to general relativity, you get this. The pink is the gas. The blue is the dark matter. Now, these clusters flew through each other. The gas interacted, got stripped from the clusters. The dark matter didn't. The dark matter rode along with the two clusters. So the dark matter did not interact with itself like the gas did. The gas interacted with itself. And so that's all we know about the dark matter. It doesn't readily interact with itself, and it curves space-time. Other than that, there's nothing that we know about it. As we move closer to home and they get data on galaxies, you can get high-resolution images of galaxies in the infrared. Now, these are, quote, color images. That what they're doing here, the reds and oranges, those are from the longer wavelength infrared, and in the blue, they're mapping to the shorter, the near infrared. So you can come up with these, quote, false color images, but that's what they're showing you here. Now with infrared, you can see structures that you're not going to see with optical light. With optical light, a lot of these galaxies have what we call interstellar dust in them, and it's hard to see the gas and the stars in parts of these galaxies. With the infrared, you can see through that, and I'll show you some examples of what I'm talking about. So infrared, good for distant things because of the redshift. Infrared is good because it gives you X-ray vision through dust. So this is handy in studying star formation. So now we're in our galaxy. So we've gone from the distant universe, and now we're in the Milky Way galaxy where we live. And this is a famous nebula in our galaxy up this time of year, the Orion Nebula. And the pinks, hydrogen gas, this is a star-forming region. There are already stars that have formed inside of this cloud. There are protostars inside of that cloud. There's a lot of dark areas in that cloud and the visible image on the right. On the left, that's an infrared image from the Spitzer. And infrared light does not interact with the dust as much as visible light. So there's an effect called interstellar reddening. So optical light, light that we see with our eyes, interacts rather strongly with the dust particles. Now, we call them dust particles in astronomy, but the size of the particles are about the same size as the particles, say, in wood smoke. So that's what we're talking about in terms of interstellar dust. That size is just right to cause a lot of scattering of light, especially blue light and ultraviolet light. It doesn't interact with infrared light nearly as much. So infrared light can go through that smoke, and you can see into these clouds deeper than what you ever could with an optical telescope. And so you can see into these clouds, and you can see the protostars. This is the center of that Orion Nebula taken with the James Webb. So you're not seeing all those dark areas now. You're seeing through that dust. You can see what's happening. This is a protostar in the Orion Nebula. And that dark thing you see there, that's a baby solar system. Planets are going to form out of that disk. And we'd like to be able to see protoplanets or evidence of protoplanets. And so one of the things that James Webb lets you do is you can penetrate deeper into that very dusty disk around this protostar, and you might be able to start to see more evidence for protoplanets that are orbiting around there as well. This isn't in Orion, but it's off in the direction of Taurus. Hubble, you're seeing there on the upper right, upper left there. That dark disk is cutting across there, and you can barely see into that disk. You're seeing that disk edge on. With infrared, you can see deeper into that disk. And so studying star formation and planet formation is going to be revolutionized by the James Webb Space Telescope. Because again, we can use it to penetrate into these clouds. This is showing you Hubble versus Webb. And you can see how much that dust extincts the starlight when you're invisible versus infrared. So you can see much deeper into that cloud. And you can see structures and protostellar objects that you otherwise wouldn't be able to see. This is perhaps the most famous of the Hubble images, right? You probably remember this when this came out. This is the so-called Pillars of Creation. This is part of the Eagle Nebula. This is just part of the Eagle Nebula. It's not the whole thing. On the left is Hubble, and you can see, you can't see very deep into that cloud because of the interstellar dust, but with James Webb, you can see deeper in, you can see a lot more structures, you can start to hunt down all the protostellar objects that are hiding out in that cloud. And then you can, over time, maybe look at what's happening in terms of changes and be able to study in more detail the star formation process. Now, the ones circled on the top there, protostellar objects, they're probably not going to become stars. There are nearby very bright, hot stars that are evaporating the top of that cloud down. And it may prevent those stars from forming. The ones that are probably going to form are the ones that are buried deep and aren't going to get evaporated away. Another place where they're seeing that evaporation happening in clouds is near the galactic center. So our supermassive black hole is there at Sagittarius A. You got this cloud over here, and there's probably some doomed protostars in there because this is a very high energy radiation area. The other thing you can start hunting for with infrared telescopes like the James Webb are objects that are too small to be stars. And one class of those are called brown dwarfs. Brown dwarfs didn't quite make weight. If you didn't make weight, you can't fuse hydrogen into helium and you're not a star. But you probably wouldn't call these things planets either. You know, they're in that gray area of planet versus star. And so they're called brown dwarfs. The reason they're called brown dwarfs is they're not very bright. they're not producing light via fusion, they're just emitting due to their temperature, and their temperature is not particularly high, so they're going to be brightest at the infrared. So if you survey the sky in the infrared, you're going to be able to pick out these dim, failed stars in some of these clouds. So these clouds are going to form stars. Some of them are going to form brown dwarfs as well. And there's going to be a whole population. You're going to have big stars, medium stars, low mass stars, and then brown dwarfs as well forming. The other sort of object, if you go smaller in weight, you get into planets. And since the mid to late 90s, we've been discovering more and more planets around other stars in our galaxy, the so-called exoplanets. Now, James Webb, its mission isn't to discover these. It's to go back and do some cleanup work in terms of figuring out what can we figure out about these planets. Which ones have atmospheres, for example? So if you got one of these planets with an atmosphere and it passes in front of its star, the starlight's going to go through the atmosphere of the planet. And that interaction is going to show up as various lines in the spectrum that we can identify in terms of what that atmosphere is made out of. So you can see things that we've got in this atmosphere of this exoplanet. We've got water. People get excited, right? You get water in the atmosphere of a planet. You got things like ammonia, carbon dioxide, carbon monoxide, sulfur dioxide, ammonia. Probably not what you want in your atmosphere, some of this, right? But this is pretty amazing that you can figure out what's in the atmosphere of one of these relatively newly discovered exoplanets. So this has that sort of power. It can collect that much light and do that sort of spectral analysis. This is an example of an exoplanet that doesn't have much of an atmosphere. This is what they think is maybe a hot lava planet. It may have a thin atmosphere, but it's not a thick atmosphere like the previous example. So this is giving us the capability of going back and doing more than just discovering these exoplanets. We can now go back and try to figure out, okay, what are they? What kind of atmospheres do they have? With that coronagraph capability in some of these cameras, like I said, that camera can block out the star, and then you can look for objects that are bright in the infrared around that star, and that's one way that they've verified some of these exoplanets. So without it blocked, you can't see the nearby object. But once you block that center star, then you can see an infrared bright object. Now it's probably something like Jupiter or larger type of object, but you're able to see it directly through imaging. Because most of these exoplanets are not discovered by imaging. They're discovered by what's happening to the star. They can detect the wobble of the star due to the planet going around it, or if the planet passes in front of the star, you notice there's a dip in the light. And so most of these aren't direct imaging. But now we're getting closer to home. So with some of the cameras on James Webb, they have been doing some studies of some of the planets, especially outer solar system. So you got Jupiter there, and one of the things that they're able to observe is the aurora on Jupiter. So the sun's been active. How many people saw the aurora here in Arkansas, or saw pictures? Some people got pictures. So that active sun is also impacting the other planets as well and causing aurora on them as well. Here's Saturn in the infrared. And there's some interesting things happening with some of these moons, especially Enceladus. Enceladus has kind of a fountain effect on it, and it's leaving a plume of material as it's orbiting around that they can see in the infrared, that you're not going to be able to see in the optical. And with the spectroscopic capability, they can figure out the composition of that material. So there's been at least one moon discovery by James Webb around Uranus. Again, that's going to be a dim object, but it's going to be brighter in the infrared, because if you're out at these distances, these are cold worlds. They're going to be brighter in the infrared than the visible. And then sometimes there are interlopers that come into the solar system. This is the Atlas object that you may have heard about in the news. It is not of our solar system, because when you look at its trajectory, it's come in from elsewhere. How many people have read Rendezvous with Rama? So, but this probably isn't a spaceship. It's probably more of a comet-like object. And in fact, they turned the James Webb to it. And so that's a James Webb infrared image of the Atlas comet interstellar object. And again, with the spectroscopic capabilities, they're able to get an essay of what's in this thing. How much water, how much carbon dioxide, carbon monoxide, things like that. This is a sample of another solar system. So when we do this same thing for comets in our solar system, we're getting information about our early solar system. Things like this, we can find out, okay, is this similar to our solar system in terms of composition? Is it different? Things of that nature. And so there hasn't been very many. This is like only the third interstellar interloper through our solar system that we know of. Of course, there's probably been lots and lots. These are very dim, hard to discover, but there's 3 that we've been able to snag so far. I'm sure there will be more, because there's other automated telescopes out there. If you've heard about the Vera Rubin telescope, it's taking full sky images every night. They're basically building not a picture of the sky, but a movie of the sky. So they're generating terabytes and terabytes of data. And what's going to be in that data are all these little things that are moving on the sky that we've never seen before. And you're going to need AI to go in there and find it for you, because there's just no way, not enough man hours to go in and visually inspect all that. So astronomy's big data. So these large telescopes, this telescope generates huge amounts of data over time. So data management is an issue. But anyways, I'll stop there. For the latest, you can always go straight to the Webb Space Telescope website. You can see what the latest news and buzz is in terms of the latest discoveries. But I'll stop there and take any questions.
Yeah, trying to get you off the way. I'll pass the mic around if y'all have questions.
I'm curious about the slide you showed of the two the interaction, the dark matter.
Yeah,
going
the bullet cluster,
through
yeah.
each other. It seems like if dark matter is warping space-time, it's interacting with gravity, is it not? But here...
It's interacting with space-time. That interaction is what we call gravity.
But the two dark matter groups, whatever they were, didn't interact with each other.
Right.
So
The gas, it interacted not through gravity, okay? So it's like the weather, right? You've got this front comes in and hits this, warm front hitting a cold front, that sort of interaction and shocks and that sort of thing. So it's not behaving like a gas, in other words.
But it's not behaving like gravity?
But it's behaving more like the cluster itself, right? The cluster, those galaxies did not appreciably interact with each other. Now, there probably was some gravitational interaction with the dark matter, just like there was probably some gravitational interaction between the galaxies. But when it was all said and done, it wasn't much.
Dark matter works in mysterious ways.
Well, the way I kind of look at dark matter is we're matter chauvinists because we're made out of matter. And so there's, quote, 4 forces in the universe. There's gravity, there's electromagnetic radiation, and there's a strong and weak nuclear forces, okay, that we know of. There could be, in this room right now, other physics that we can't interact with because it interacts with other forces that we don't interact with. And that could be what dark matter is. It could be a form of something that is operating through other forces that we don't operate with. Because the only way that we know about anything else in the universe is we have to interact with it either gravitationally or through electromagnetic radiation, or in certain cases, a strong and weak nuclear force. But if the universe is more than that, but we can't interact with it other than maybe through gravity, we're not going to be able to find out much about it, if that's the case. But that's just my hypothesis.
What's the difference between supermassive dark hole and a regular black hole?
Size is everything. So what we call stellar mass black holes, you're looking at like 10 solar masses, 100 solar masses, stuff in that area. And then supermassive, then you're into millions or billions. Of course, you can imagine, and there is a category of intermediate. So if you're thousands but not millions, you're into the intermediate size. We don't have very imaginative names for things in astronomy. It's either Big Bang, black hole, dark matter. It's not very imaginative.
So are all galaxies then held together by, is a definition of a galaxy a black hole holding together a collection of solar systems? Or
well, so that's a good point. So just our galaxy as an example, so what's holding it together is the gravity of everything in it. It's not just the black hole, even though billion sounds like a lot. There's hundreds of billions of stars in the galaxy, so it's still a tiny fraction of the whole thing. So what's holding our galaxy and other galaxies together is the combined warping of space-time of all mass in that galaxy, including dark matter. And in fact, that's one of the things that people noticed that led people down the road that there had to be dark matter. You look at how fast stars are orbiting at the outside of our galaxy, on the edge of our galaxy, or out at the edge of other galaxies. They're moving so fast that if it's just the mass of the things you see, that stuff should be flung out of the galaxy. That's what led them to do the calculation and go, there's got to be some unseen something in these galaxies. And so now we've got lots of different things pointing at there's more stuff that's warping space-time in the universe than the stuff we see.
Are we seeing any evidence of solar systems existing outside of galaxies, or is it pretty much?
Well, that's tougher to do. So solar systems outside of the Milky Way, I think there's been some detections in either the small or the large Magellanic Cloud, which are small galaxies that are orbiting the Milky Way. We don't have telescopes big enough to do the same sort of observations we're doing in our galaxy to even the Andromeda Galaxy, which is the nearest galaxy similar to our galaxy. So you're looking at 2.5 million light years away. So again, we want bigger and bigger telescopes. Hubble allows you to look at Cepheid variable stars and some of these other, but those are bright stars. But if you want to see what's happening with a sun-sized star, even in the Andromeda Galaxy, we don't have telescopes big enough.
So pretty much everything we're looking at is through the Milky Way. Is that what you're saying?
Well, it depends on what you're studying. If you're these exoplanets, those are almost all exclusively in our galaxy because of the limitations.
So there's a possibility of having two telescopes separated by a large distance, coordinating and having an effective larger.
Yeah, so what he's talking about is something called interferometry. You don't get the light gathering capacity, but you do get resolution improvement. So if you had 2 of these James Webbs separated by a certain distance, and if there's a way to combine that light as a single telescope, then you would improve your resolution. The downside is you're probably still not going to be bright enough to see some of these things real well. But if you had enough of them,
We do that with radio telescopes now.
radio telescopes, and we do that now with some, there are some optical interferometers. There's one in Arizona near Flagstaff that's been operating for probably going on 30 years now, and there's been some others. They're not looking at dim stuff. They're looking a lot of times at binary star systems, the stars that are pretty bright. But because of the high resolution, they're able to see 2 stars that are really close together in the sky. But what he's talking about, interferometry and radio has been done for a long time. Because it's a lot easier to combine those signals than it is optical signals. So they use optical fibers to do the light combining. And just like you have to with the radio telescopes when you do the combining, the cables have to be the same length, right? So you have to have the optical fibers be the same length so that what's coming to the telescope, you're detecting the same time or the time difference and all of that. But, yep.
I guess one of the things you mentioned, finding supermassive black holes in the early universe. You didn't really touch much on why that's surprising.
Well, what's not understood about any of these supermassive black holes is how do they form? Obviously, they form from a lot of smaller stuff getting together, but we don't know exactly that process. And that's one of the things you'd like to be able to see back in time to see that process happening. So if it's multiple black holes that you're forming with supernova explosions, that takes some time, right? You got to be able to form these smaller black holes, and then you have to have a mechanism where somehow they coalesce. And that all takes time. And unlike a common misconception about black holes sucking, they don't suck in the way you think. For example, if I could snap my fingers and make the sun a black hole of the same mass as the sun, our orbit would not change. We would not get sucked in. The only way you get sucked in is if you slow down your velocity enough so that you get sucked in. So you're talking about things that are going to take time if you're going to have several black holes somehow coalesce together. And they're seeing stuff happening sooner than they would predict.
I guess what I was referring to is that there's limits on the growth rate because of the radiation pressure of stuff falling in.
And that's all stuff that they're looking at and going, oh, well, how in the 400,000 years since the start of the Big Bang can you have a supermassive black hole? Those are all that physics comes in. Some people point to maybe these don't form by multiple black holes. Maybe it's a process where these form all at once somehow. So instead of forming a star and waiting for the star to do its thing before you form the black hole, maybe somehow you get a huge collapse of a lot of matter all at once, would be the other thing. But like you said, you got radiation pressure issues and stuff. And
Dark matter is thought to be some of the ways you can form a lot of supermassive.
And then maybe that's it. Maybe dark matter are the seeds for that. Okay, dark matter seems to certainly be the seeds for galaxy formation. I was staring at this thing. If you map out the dark matter in the universe, it's like the branches. And then the galaxies are like these candles.
So if my goal was to produce an image of an exoplanet on par with, say, the picture the Apollo astronauts took of Earth from the moon.
You're like Al Gore.
Ambition, right?
No, if you remember, Al Gore, that's one of the things that he was proposing that we should do. So he was proposing, let's do a telescope large enough in diameter that A, you can collect enough light to see it, and B, be able to see some detail. Now, of course, you're talking, you may have to do some sort of interferometry type thing like he was talking about, but a number, I don't have a number off the top of my head, but you're looking at a huge aperture telescope.
Yeah, I remember Neil deGrasse Tyson on the Cosmos series, this is the reboot of it, saying that, you know, we have the technology now to build a gravitational lensing telescope, so why don't we do it? And I wonder if that's a better approach to take the picture I want to see, or if launching a dozen more copies of the Webb Space Telescope would be the more economical solution, because most of the expense was in designing it. The next dozen would cost less than the first one.
But you gotta get funding through Congress, but yeah, these aren't cheap things to do. And
Excuse me, so much of the stuff is theoretical. Vera Rubin's paper in 1985 is the sole basis upon which the whole concept of dark matter came about. It's never been observed in the last 40 years in any laboratory or anything like that. It's theoretical. And even with Hubble, I mean, all of Hubble's works, his initial paper in 1929, the seminal paper, was only over a short distance. However, the concept of light, and in fact, after the early 30s, until his death in 1954, Hubble never believed himself that the universe was expanding. In fact, he spent about 25 years, his last 25 years of life, trying to figure out a method to prove that the universe was not expanding. And he always prefaced any concept of an expanding universe was if you assume certain things, the universe was expanding. But all of his later work was, only by a year or so that he thought that the universe was expanding.
So Einstein was.
There's so many unanswered questions, even with the black holes and everything else.
So according to you, Einstein is incorrect?
Pardon?
So according to you, Einstein's general relativity is incorrect?
No, I never said that.
I'm hearing a lot of that from what you're saying.
What we're saying, Hubble was saying
Well,
that
Hubble wanted to believe, like a lot of people believed at the time, that the universe was static, which gave Einstein fits. Because general relativity, if you start trying to build a model universe with general relativity, the damn thing either wants to collapse on you or expand on you. It doesn't want to be stable. So this is why he put in the cosmological constant into his equations. And then when Hubble came around with the evidence that the universe was expanding, Einstein was elated. Because it's like, God damn it, I can get rid of this cosmological constant thing that I had to shove in there. But it turns out, in the modern equations, I didn't even talk about dark energy, but there's the accelerating universe where you need a cosmological constant term in your general relativity. So I'm with you that there's things that we haven't figured out.
just a couple more questions.
So general relativity is not completely correct because it doesn't work with quantum physics. So it's not completely correct.
Or is quantum mechanics incorrect because it
One of them isn't quite right.
So yeah, something isn't quite right, because if at high temperatures and densities, you would think general relativity and quantum mechanics ought to be together. You ought to be able to write down physics equations that describe what happens at those levels.
Need more data. Yeah.
Well, the other thing is, if you look at what we do, especially in physics, we come up with ways to make predictions. So if it works, we say it's correct, right? Until it doesn't work. You know, Newton works great. Newton can get you to the moon, can take you to Mars, but if you look at certain phenomenon, Newton doesn't work. The precession of the orbit of Mercury around the sun is not predicted by Newton. It's predicted by Einstein's general relativity in curved space-time. So is Newton wrong? Depends on what you're trying to do. So if you're just trying to get to the moon, you don't need to put in relativistic effects. But depending on what you're doing, you may need to put in relativistic effects. So if you use GPS to navigate here today, you use general relativistic corrections. That's how GPS works. GPS works with clocks. Clocks near the surface of the Earth tick slower than ones that are further from the surface of the Earth due to the difference in the curved space-time. But what's correct and what isn't correct? I don't know. In physics, it's what's good enough, what allows you to do the predictions. Is there a single answer? I don't know. Are we capable of coming up with a single answer?
Could you go back to what you had said about the dark matter kind of representing the shape of that tree? Is that really kind of caught my ear?
So if you so they've done maps of dark matter in the universe that cover a lot more of the sky than this. And so what you find is the dark matter is a web-like structure throughout the universe like this. And where you find galaxies and galactic clusters are along the branches here, just like this thing. There's places in our universe that, in terms of matter and galaxies, you don't see anything. There's these huge holes throughout the universe that are called voids. And you don't see dark matter evidence for there. You don't see galaxies in those regions. So the dark matter seems to be the skeleton for the stuff that we see. Which makes sense, right? If dark matter is curving space-time, that could accelerate things like galaxy formation, stuff like that. So it hangs together from that standpoint. Again, you'd like to have a mathematical description of what the heck this stuff is, but it's very limited right now.
Maybe the Vikings are onto something.
The what?
Maybe the Vikings are onto something.
Vikings?
Sure, get interested a little.
Oh.
All right, well, thank you, everybody. Let's give
Thanks.
Well, my brain is expanding along with the universe, because that was a great presentation. Thank you very much. Yeah. We've got Pint Night coming up tomorrow at the Flying Saucer, 7 p.m. You're all invited, including those of you in YouTube streaming land. The ASF board meeting is the following night, Tuesday, and instructions are online if you'd like to join in with that. We have additional meetups available on our meetup.com app, including there's a Conway potluck and meet and greet scheduled for Saturday, February 21st. And so if you live in the Conway area, have friends out there, that's a great one. We're trying to get some activities going, not just here in Little Rock or North Little Rock. We have an ASF book club now. We're going to be, we have the ASF book club meeting on Sunday, February 22nd. More details are back there. There's a sign-up sheet if you're interested in getting in the loop on that book club and would like to read interesting books with interesting people. Fourth Monday Discord chat is Monday, February 23rd. And we have First Tuesday coming around at American Pie Pizza in North Little Rock, as always, on the first Tuesday of the month on March 3rd. And then it is Second Sunday Cantina Communion on the second Sunday of March, March 6th. And that is at Cantina Cinco de Mayo down on Stagecoach Road. All this is available in the Meetup app. This is your way to keep in touch with things that are going on. It's what I'm reading off of here, and you can be as well informed as I am just by following the Arkansas Society of Free Thinkers. But for those who don't have space for another app along with your Instagram, your TikTok, and all the other important things, then you can always just navigate to arfreethinkers.org where we have a calendar. And while you're there, please join or donate to our organization, because our hosting fees, equipment, banking fees, everything costs money, and we keep this organization, we run a tight ship, but we also need revenue coming in. One free thing that you could do that's absolutely no cost to you whatsoever is if you shop at Kroger, navigate on their website, log in, and then navigate to Kroger Community Rewards. And then look up the Arkansas Society of Free Thinkers. We are a nonprofit 501c3 providing services such as this public education event. And you can actually sign up to have Kroger donate a portion of their budget on your behalf based on your spending at Kroger. It doesn't come out of your spending, it comes out of theirs. So we actually earn a decent amount of revenue. I've just deposited 3 $40 checks. So, you know, that kind of thing is just a passive thing that you set it, forget it, and it helps the organization. I would appreciate it if you'd all do that. And are there any other announcements anyone would like to make while we're here?
Something happens on second Sunday, I think. What is that?
Yeah, Second Sunday Cantina Communion that I mentioned is on March 8th. Yeah, and generally asking me is a less efficient way than just getting the app, but you know, we work with everybody. It's fine. Well, thank you all for joining us, and I look forward to seeing you at First Tuesday, at Pint Night tomorrow night, at Cantina Cinco de Mayo, at all the events that we have on the calendar, and please join and support, and I look forward to mingling after the meeting. Thanks.
Thanks,